Okay, this tutorial is going to start with section 4.1, and that's factoring the difference of squares and trinomial squares. In your textbook, they give you a good definition of a trinomial square and a difference of squares. If you look at the two definitions, they give you a nice little box on page 109 for the difference of squares, and that's basically two terms that are perfectly squared and have a difference in them. And they give you a definition of a trinomial square on page 113, which basically has three terms, and the perfect squares are at the beginning and the end, where the middle term is double the square roots of those two terms. And also they have a sign pattern that's very specific. The two positive terms have to be at the end. Doesn't matter what the middle term is. Okay, so what we're going to do is we're just going to do some examples here of those things. So we're going to start with the difference of squares. So my first example here is 4 minus 9b squared. So this would be a difference of squares, a perfect square for the first term and the second term, and there's a difference in them. So that will basically break down into two binomials of different signs, where the square root of the first term is the beginning of each binomial, and the square root of the final term is the end of each binomial, with the signs in between being different. So what you do there is you put your binomials out. Square root of 4 is 2, and the square root of 9b squared is 3b. So that would be our two terms, and then because it's a difference of squares, one is positive and one is negative. So that's basically how you do the difference of squares. However, you may get a little more complex example where you have to do common factors. So let's say we had 98a minus 72a cubed. So we can see here there are common factors between each term in the binomial here. So what we'll look at to do is take out the biggest common factor we can find, and in our case it's 2a. So always take out your common factor first. So if you take out 2a from 98a, that's 49. And you take out 2a from 72a cubed, that's 36a squared. So we can continue this one, pardon me, by looking at this as being a difference of squares now. Keep the 2a here, set your two binomials that you're going to get. The root of 49 is 7, and the root of 36 is 6, and the root of a squared is a, so that's 6a. And because it's a difference, one is positive and one is negative. That would be our next example. So let's take a look at another example with a common factor. If we had m minus 16m cubed, again here we only have m as our common factor. Take out the common factor. And we can see that this 1 is a perfect square and 16m squared is a perfect square. So our two binomials will be the root of 1 is 1, the root of 16m squared is 4m, and different signs. Okay, we're going to also look at an example where you might have a special case. Sometimes they give you a binomial squared in that form. Let me just check my field of view, make sure we're still doing all right. Okay, so what we'll look at now is sometimes you get an example that may look something like this. They would give you a binomial here, say, let's make it simple, x plus y all squared minus 9. This is still a difference of squares because this binomial is squared and this is a perfect square number. So you use the same method that you would use in the previous past. However, to make it simpler, if you can't remember x plus y is your binomial, sometimes you can replay that by using a secondary variable. So it really is up to you if you want to use a secondary variable, but if we're going to use a secondary variable, usually they're capitals. So let's make it capital W is going to equal x plus y. So if I were to rewrite this expression then, capital W minus 9. And of course capital W squared. So now we could say that, well, that's just a difference of squares. That's capital W and 3, capital W and 3, and a difference of squares. And then we just simply replace x plus y where W is. Now if there were a number in there, you could still do some reducing inside the brackets. And that would be an example of a difference of squares that has the use of a secondary variable. So now we're going to look at trinomial squares. Now trinomial squares have 3 terms in them. So let's look at an example of a trinomial square here. So I've got 9a squared minus 6a plus 1. So when you're looking at trinomial squares, they work into 2 binomials with the exact same sign. And they have to have the sign pattern of plus, 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 or plus, minus, plus. The 2 outside ones have to be plus, and also the 2 outside terms have to be perfect squares. And the middle term is going to be double the product of the root of both of those squares. So if you look at this, we would just take the 2 and say to ourselves, well, the root of this is 3a. And the root of 1 is just 1. And because the sign in the middle is a negative sign, this would give us a negative sign for our both our binomials. Now with a trinomial square, you have the same sign in both binomials. So let's just check this. This would be 9a squared, and this would be negative 3a, and this would be negative 3a, which would give us negative 6a, and a positive 1. Okay, so let's combine what we know now of trinomial squares and binomial squares, and let's combine them together to do a problem that might look something like this. Say I had something like 25, x squared minus 20x plus 4 subtracting 81y squared. Seems a bit confusing, but if we were able to recognize that this here trinomial is a perfect trinomial square. This is a square root, and this is a square root, and our perfect square, I guess, and we could take the square roots of them and combine them to get the middle term. So what we can do there is break this down, leaving our 81y squared here. Okay, breaking this down, the root of 25x squared is 5x. And the root of 4 is 2. So the product you have to get, the middle term has to work out here. So we have to make sure that we're checking to see if the middle term is actually working out. And we also have to be aware of, because there's a negative sign there, we're going to have negative signs in here. So if we did that, we'd get 5 times negative 2 is negative 10, and negative 2 times 5 is negative 10x. So negative 10x and negative 10x gives us our negative 20x. So then if we were to rewrite this, we could say 5x minus 2 all squared would be those 2 things perfectly squared. So then we have an example that is similar to this example that we did up here. So we can use a capital W or another capital letter. I'm going to use a capital A this time to equal the 5x minus 2. So we go a squared minus 81y squared. Perfect square of a squared is a. Sorry, pardon me, that would be the perfect root of that. So we have a and a there, and we take the square root of this to get 9y. And of course, because of the minus sign in there, no middle term, 1 is positive and 1 is negative. And then we can plug back in our numbers. Here I'm working near the bottom. I'm going to check by field of view. Okay, and to finish this off then, we just plug in back our numbers from A. And that would be our example, our example of the factoring of trinomial squares and differences of squares. In our next section, we'll be looking at factoring as well, and specifically we'll be looking at cubes.